Hello friends, welcome to Akul Mac Live. Today we are talking about the latest discovery by James Webb Space Telescope. It is groundbreaking. In this video we will explore the shocking find, a planet orbiting a pulsar, which is basically is a neutron star, and this planet's atmosphere, which is almost entirely made of carbon. Join me as we uncover the secrets of this unique exoplanet, a celestial body unlike any we have seen before. We will discuss how JWST's incredible technology made this discovery possible, and we will understand what is a pulsar, the implications of finding a planet with such an exotic composition. Therefore, don't miss out this journey to the edge of the space and science. Welcome, space enthusiast, to a journey into the cosmos that promises to redefine our understanding of the planetary formation and the sheer diversity of the worlds beyond our own. Today, we are diving into a truly astonishing discovery, one that has sent ripples of excitement through the scientific community and captivated the imagination of the stargazers worldwide. We are talking about a planet unlike any other, a celestial marvel found orbiting a dying star with an atmosphere that defies conventional expectation, a carbon planet. And who better to bring us this revolutionary insight than the marvel of the modern engineering? And that is the James Webb Space Telescope. Before we plunge into the heart of this carbon rich world, let's take a moment to appreciate the instrument that made it all possible. James Webb Space Telescope, or JWST, launched on Christmas Day in the year 2021. JWST is not just a telescope, it's a cosmic detective capable of peering back in time to the universe's infancy, observing the birth of stars and galaxies, and crucially for our story today, meticulously analyzing the atmospheres of distant exoplanets. Unlike its predecessor, the Hubble Space Telescope, which primarily observes in the visible and ultraviolet light, JWST is an infrared observatory. Why is infrared so important? Well, infrared light can penetrate through the thick dust and gas clouds and that often obscures the visible light, revealing the hidden wonders. It also incredibly sensitive to the heat signature and the molecule composition of the planetary atmosphere. Imagine trying to see through a dense fog with your eyes. Now imagine having special glasses that allows you to see the heat radiating from objects within that fog. That's essentially what JWST does for us in space. Its massive gold-plated mirror spanning 6.5 meters act like a giant light bucket, gathering the faint infrared glow from incredibly distant objects. This allows scientists to perform a technique called transit spectroscopy. As a planet passes in front of the host star, some of the star's light is filtered through the planet's atmosphere. By analyzing the subtle changes in this light, specifically when the wavelengths are absorbed, scientists can deduce the chemical makeup of the atmosphere. And it was this precise, painstaking method that led to our extraordinary discovery. Now let's turn our attention to the unusual host of this carbon planet, a pulsar. The very word pulsar evokes imagination, and also it gives you a feeling of the cosmic power and mystery. For a good reason. Pulsars are not your average stars. They are collapsed, rapidly spinning remnants of the massive stars that have met a spectacular end in the supernova explosions. Imagine a star far larger than our Sun burning through its nuclear fuel at an incredible rate. When it finally exhausts its fuel, its core collapses under its own immense gravity, forming an incredibly dense object. If the star was massive enough, this collapse can lead to formation of the black hole. But if it was slightly less massive, it becomes a neutron star. And if that neutron star was rotating rapidly, it has a strong magnetic field aligned to in a particular way, and therefore it becomes a pulsar. Pulsars are essentially cosmic lighthouses. As they spin, they emit beams of intense radiation in radio waves, X rays, and even gamma rays from their magnetic poles. If one of these beams sweeps across Earth, we detect a regular pulse of radiation, much like a lighthouse beam sweeping past a ship. These pulses are incredibly precise, often to within milliseconds, making pulsars some of the most accurate clocks in the universe. But don't let their precision fool you. Pulsars are also incredibly violent and energetic. They also have energetic environment. The radiation they emit is powerful enough to strip away the atmosphere of nearby planets or even sterilize any life that might attempt to form in the nearby area. So the idea of finding any planet orbiting a pulsar is remarkable in itself. But to find one with an atmosphere entirely made of carbon, that is truly unprecedented. The story of this discovery begins with routine observations. Scientists using JWST were initially targeting a known pulsar, perhaps to study its properties or search for subtle gravitational anomalies. As the JWST focused its keen infrared eyes on this distant beacon, a faint periodic dip in the pulsar's light was detected. This dip, repeating with uncanny regularity, was the telltale sign of the planet transiting or passing in front of the pulsar. The initial excitement was palpable. Finding a planet around a pulsar is a rare event, as the intense supernova explosion that creates the pulsar is usually thought to be very violent, and any pre-existing planetary system will get completely destroyed. So these planets are often second generation, formed from the debris left over after the supernova. But the real shock came when the team began to analyze the light passing through the planet's atmosphere during these transits. Using the JWST powerful spectrometers, they meticulously broke down the light into its constituent wavelengths. What they saw was not what they expected. Typically, when we analyze the exoplanet atmospheres, we look at the signatures of common elements like hydrogen, helium, water vapor, methane, or carbon dioxide. These are building blocks of the gaseous giants and rocky world we are familiar with. But the spectrum from this particular planet was almost entirely dominated by carbon. Imagine a puzzle where most of the pieces are missing, but the few pieces you have all clearly show the same image. That's what the scientists experienced. The data pointed overwhelmingly to an atmosphere rich almost exclusively in various forms of carbon. This wasn't just a planet with some carbon, this was a carbon planet. So, what exactly is a carbon planet? To understand this, let us first consider the Earth. Our planet is rich in silicates, forming its rocky mantle and crust. Carbon is also present, of course, in organic life, in our atmosphere as carbon dioxide, and in geological formations like limestone. But it is not the dominant element in our planet's bulk composition. A carbon planet, in theory, is a world where carbon is much more abundant than oxygen and other elements that typically form rocky planets. This means that instead of having a silicate mantle and an iron core, a carbon planet might have a mantle composed of various forms of carbon, from graphite to diamond and potentially an iron carbide core. The implication of such a compositions are profound. For instance, if the conditions are right, The immense pressure and high temperature part of such planet could literally be made of diamond. We have long theorized about diamond planets as a fascinating possibility, but this discovery by JWST provides the first tantalizing evidence of a world where carbon truly reigns supreme in its atmosphere, hinting an equal carbon rich interior. The atmosphere itself, being almost entirely carbon, presents a completely alien environment. While we don't yet know the exact form of the carbon present, whether it's mostly carbon monoxide, carbon dioxide, or more exotic carbon compounds, the absence of significant amount of other common atmospheric gases makes it truly unique. This isn't just a slight variation, it's a fundamental difference in the planetary chemistry. This brings us to the crucial question: how does such a planet form, especially around a pulsar? The conventional wisdom is that the planet formed from the protoplanetary disk of gas and dust surrounding a young star. A composition of this dust dictates the type of planet that forms. In the case of this carbon planet around a pulsar, the most compelling theory involves the aftermath of the supernova explosion. When the massive star explodes, it blasts enormous amount of material into space. This material, rich in heavy elements forged during the star's life and death, then mixes with the existing interstellar medium. However, the key here might be the type of star that becomes a pulsar, or perhaps an earlier binary companion star. If the original star system had a specific chemical composition, for instance being particularly rich in carbon and relatively poor in oxygen, then the debris cloud left over after the supernova would also be carbon rich. Imagine a scenario where a white dwarf star, which is essentially the core of a star like our sun after it has shed its outer layers, was in a binary system with a star that eventually became a pulsar. If this white dwarf was a carbon oxygen white dwarf, as many are, then suffered some of the form of disruption or accretion into the neutron star, it could provide the necessary carbon rich material. Another possibility is that the pulsar itself, through its powerful radiation and magnetic field, somehow processed or enriched the surrounding dust and gas, favoring the formation of a carbon compound. This is more speculative idea, but the extreme environment around a pulsar certainly makes for a unique chemical interaction. Regardless of the exact mechanism, the formation of this carbon planet around a pulsar highlights the incredible resilience of the planet formation process. Even in the violent cosmic crucible surrounding a dead star, a new world can arise, taking an entirely unexpected composition. The discovery of this carbon planet has profound implications for planetary science. Firstly, it expands our understanding of the sheer diversity of the exoplanets. For decades, our model of planets' formation were largely based on what we observe in our own solar system. But with every new exoplanet discovery, especially those by JWST, we are realizing just how varied and surprising the universe truly is. The carbon planet challenges our assumption about the building blocks of the planet. It suggests that if the initial condition of the protoplanetary disk are sufficiently carbon rich, entirely different type of world can form with chemistries unlike anything we have previously encountered. This could open up new avenues for theoretical modeling and observational search for similar worlds. Secondly, it provides a unique laboratory for studying extreme atmospheric chemistry. An atmosphere almost entirely composed of carbon under the intense radiation of a pulsar is a fascinating subject for astronomical research. What kind of complex carbon molecules might form in such an environment? Could there be exotic form of carbon or carbon rain or carbon snow on such world? There are questions that will undoubtedly fuel years of research. Thirdly, and perhaps most intriguingly, this discovery touches upon the very definition of the habitability. While a pulsar intense radiation likely makes this specific planet inhospitable to life as we know it, the mere existence of carbon planet raises questions about life's potential and also adaptability. If the carbon is so abundant, could a different type of biochemistry entirely centered around carbon based processes evolve in a more benign carbon rich environment? It's a speculative thought, but one that broadens the scope of astrobiological inquiry. Furthermore, the ability of JWST to make such a detailed atmospheric analysis is a testament to its groundbreaking capabilities. This discovery is just the beginning. As JWST continues its mission, we can expect it to uncover even more exotic worlds and provide unprecedented insight into their compositions, helping us piece together the intricate puzzle of the planetary evolution across the cosmos. So, what's next for the study of this carbon planet and exoplanet in general with JWST? Initial discovery is just the first step. Follow-up observation will be crucial. Scientists will want to obtain even more detailed spectral data to pinpoint exact form of carbon present in the atmosphere. Is it primarily carbon monoxide or more complex organic molecules? What are the temperatures and pressure profiles of the atmosphere? They will also be looking for any sign of other trace elements that might be present even in small quantities to further refine their understanding of the planet's formation and its history. Understanding the atmospheric dynamics is also important. How the wind blows, how heat is distributed, will also be key to building a complete picture of this unique world. Beyond this specific planet, JWST will continue its relentless search for exoplanets and their atmospheric signature. Its ability to characterize the atmosphere of even smaller rocky worlds in the habitable zone of their star is unparalleled. This means we are on the cusp of truly understanding which exoplanet might possess the condition favorable to life. The telescope's deep field observations will also allow us to study exoplanets in very different environments, including those around the red dwarf, which are most common stars in our galaxy, and even rogue planets that wanders through space and they are not attached to any star. Each new discovery will add another piece to the grand mosaic of the planetary diversity. The discovery of carbon planet around a pulsar by the James Webb Space Telescope is more than just a scientific announcement. It's a testament to human ingenuity, perseverance, and our ability to search the universe. This carbon planet is a beacon, a cosmic signpost pointing towards a new frontier in exoplanet search. From diamond rich interiors to atmospheres unlike anything that we have found in our solar system, the potential for the discovery is boundless. JWST has opened a new window into the alien worlds. So, as we continue to explore the vast expanse of the space, armed with powerful instruments like JWST, we are not just observing distant objects, we are extending our understanding about the universe. The carbon planet found by JWST around the pulsar is a testament to the fact the universe is far stranger, far more diverse, far more fascinating than we could have imagined. So, friends, thank you for joining me on this cosmic journey. Stay curious, keep looking up, and remember that every night the universe is revealing its secret, one extraordinary discovery at a time. See you in the next one.